All right. Hello, everyone. Um, Welcome back for week 10 of Maps, Mapping, and Geospatial Technology. Today we'll be talking about cartography and maps. So, what is cartography? It is the art of science and map making. One thing that makes spatial data unique is that it can be mapped. Once you've used GIS to create the boundaries of a Civil War battlefield and analyzed its proximity to new housing and commercial developments, the next step is to make a map of the result of your work. However, making a good map with GIS involves more than taking the final product of the analysis, throwing on a title and legend, and clicking on print, and then calling it a day. Numerous design elements and consideration should be taken into account when you're laying out a map. In fact, there's a whole art and science of map making called cartography, involving things such as color selection, the positioning of items on the map, and the kind of message the final map product is intended to convey to the reader. A map is a spatial representation of the environment presented graphically. This is a quote from Kimmerling. This is part of the visual hierarchy of the map, which contains what most elements of the map are most important and thus most prominently displayed, and what information is less important. A poorly designed map is still going to be a map, but a well-designed map will be more useful. Think about different maps you have encountered. Forget the geospatial component for a moment, but remember the font size, the font itself, colors, and so on. How can the design of a map influence the way the map's information is perceived by its reader? And what if a land mass was blue? Second, if the information on the map being effectively conveyed to the map reader. For instance, if you're designing a trail map, should all trails be named or marked? Or will that cause too much congestion and clutter? Will the colors and symbols be easily understood by novice map readers, or just want to find their way around the park? The trail map will likely not need an inset map of the surrounding area, but the park to put the park into a larger context, but the map reader should not be left guessing the meanings of the symbols used on the map. Scale is a basic map item, is information about the scale of the map, and there are a couple of different ways of thinking about scale. First, there's the geographic scale of something. Things that take up a large area of the ground or have large boundaries would be considered large in terms of geographic scale. Study of a global phenomenon occurs on a much larger geographic scale than study of something that exists at a city level, which would be a much smaller geographic scale. Map scale, on the other hand, is a value representing that X number of units of measurement on the map equals Y number of units in the real world. So imagine that you are a jogger and you want to determine how far you ran in today's workout. You measure the jogging path on a map. The path is 150 milliliters long. The scale of the map is 1 to 24,000. What is the length of the real jogging path? So in order to figure this out, there's a formula for it. So the map scale is 1 over 24,000 equals 150 millimeters. That's the ground distance. So the ground distance would be 24,000 times 150 millimeters, which then results in a measurement of 3.6 million millimeters. In other words, you jogged 3.6 kilometers. There's 1 million millimeters in a kilometer, and therefore there is an equivalent fraction. So 1 over 24,000 would equal to 150 divided by 3.6 million. There is that formula. 3 methods for expressing a map scale. This relationship between the real world and the map can be expressed as a representative fraction. An example of an representative fraction would be a map scale of 1 to 24,000, which means a measurement of 1 unit on the map would be equal to 24,000 units in the real world. For instance, 1 inch on a map would be the same as 24,000 inches in the real world. 1 foot on the map would be equal to 24,000 feet in the real world, and so on. Maps are considered large-scale maps or small-scale maps, depending on that representative fraction. Large-scale maps show a smaller geographic area and have a larger RF value. For instance, a 1 to 24,000 scale map is considered a large-scale map. Due to the larger scale, it shows a smaller area. Largest scale map you can make is 1 to 1, where 1 inch of the map is equal to 1 inch of measurement in the real world. That is, the map will be the same size as the ground you're actually mapping. So the map of a classroom will be the same size as the classroom itself. Conversely, a small scale map has a smaller RF value, such as 1 to 250,000, and shows a much larger geographic area. The larger the scale, the more opportunity for features to be shown. Error is also less based on scale. Consider if you are off by a centimeter, that doesn't have as much of a significance. On a slightly larger scale map, more cities are likely to be shown as points, along with other major features, such as additional roads shown as lines. Error increases. For instance, on a very small scale map, such as the one that shows the entire United States, cities are represented by points and likely only major cities are shown. With a smaller scale map, you have to represent features more simplified. This kind of cartographic generalization, or the simplification of representing items on a map, affects the data you can derive from it. Airports are a great example. Large-scale maps may show specific runways, whereas small-scale maps may just represent it as a point. Then there are some design elements. So several elements should show up on a good map. For instance, someone reading a map should be able to figure out the scale of the map fairly quickly. A map element might simply be text of the RF, such as 1 to 24,000, or 1 to 100,000, or some other map scale. A scale bar is a graphical representation of equivalent distances shown on this figure. This would be the scale bar. Second map element is the north arrow, a graphical device used to orient the direction of the map. However the map is oriented, the north arrow is used to point in the direction that is due north. A north arrow may sometimes be drawn as a compass rose, which shows all cardinal directions on the map. North arrows can be as simple as an arrow with the letter N attached, or they can be complex works of art. This would be the north arrow, so north is facing this way. Another item is the map's legend, a guide to what the various colors and symbols on the map represent. Good legend provides a key to the symbology of the map. Because the legend is the art of the map, where you can explain things to the map's reader, you might want to call it something other than legend. Instead, consider calling the legend something more useful, like park trail guide or county population change. In GIS, a map is put together by assembling all of the elements together in a layout. A good way to think of a layout is as a digital version of a blank piece of paper on which you'll arrange the various map elements together in a cartographic design to create a version of what will ultimately be your map. Sometimes mapping software such as ArcMap or QGIS includes several map templates, which provide pre-created designs for your use. A template places things like the title, legend, and north arrow at predetermined locations and sizes on the layout, no matter what GIS data you insert. Templates are useful for creating quick printable map layouts, but in some cases you might want to design a map the way you want it with regard to size, type, and placement of elements. Mention that acknowledgement is optional. So then there are several different types of maps. Of these different types of maps, they can be made using GIS tools. The purpose of a reference map, such as a road map or a map of an atlas, is to give location information and to highlight different features. A map of park trails, a Manhattan restaurant guide map, a map of the casinos on the Las Vegas strips, and a zoning map of your neighborhood are all examples of reference maps. Topographic maps are another example of reference maps. Another main type of map is the thematic map, which is geared towards conveying one particular theme to the reader. Thematic maps can be used to show things such as the state-by-state increase in U.S. population over a particular period or presidential election results county by county. In order to display this information at its best on a map, the data will have to be classified or divided into a few categories. GIS gives several options for data classification of multiple values. Each method classifies data differently, which can result in some very different results being displayed on the maps. For example, figure 7.8 shows 4 different maps of the percentage of the total number of houses per state that are considered seasonal homes or vacation homes based on census data, each created using a different data classification technique. Note that each map has the data broken into the same number of classes for comparison purposes. Also, keep in mind that choropleth maps already have the boundaries of their polygons set in place because elements such as the state's boundaries are already defined and the attributes being mapped do not define these boundaries. For instance, the state's boundaries are already delineated and the choropleth map is showing a classification of a value of seasonal home percentages utilizing all of these predetermined boundaries. The first of these data classification methods is called natural breaks. As the name implies, this method involves taking all the values being mapped and looking at how they're grouped together. The spaces in between the data values are used to make different classes of ranges of data that are displayed, as shown in figure 7.8a, which is based on natural breaks. States with the lowest percentage of states with the lowest percentages of seasonal home values, such as Nebraska, Oklahoma, and Texas, end up in one class, and states with highest percentages of seasonal homes, such as Maine, Vermont, and New Hampshire, end up in another class. The map in figure 7.8b shows the results of using quantile method of data classification. This method involves taking a total number of data values to be mapped and splitting them up into a number of classes. This method distributes values so that each range has a similar number of values in it. For instance, with 50 states being mapped, plus the District of Columbia as a 51st area, each of the 4 ranges will have about 13 counties worth of data being shown in each class. Because the breakpoints between the ranges are based on the total number of items being mapped, that is, the number of states ending up in each range, rather than the actual data values being mapped, the quantile method causes a relatively even distribution of values on the map. The third method is to use equal intervals for data classification. This is shown in 7.8c. It works as it sounds. This method involves creating a number of equally sized ranges and then splitting the data values among these ranges. The size of each range is based on the total span of values to be mapped. For instance, in the seasonal home map, the data is divided into 4 classes, and the range of values goes from the state with the lowest seasonal home percentage, 0.6% of the total housing stock in Illinois, to the state with the highest seasonal home percentage of 15.6 in Maine. The equal intervals method divides the complete span of data values by the number of classes, and that value is used to compute the breaking points between classes. Therefore, the first class represents states that have a seasonal home value of 3.75% more than at the lowest end. Note that for this method, simply classifies data based on the range of all values, but does not take into account clusters of data or how the data is distributed. Therefore, only a few states end up in the upper class because their percentages of seasonal homes are greater than 3/4 of the total span of values. The final method uses the concept of standard deviation as seen in figure 7.8d. Standard deviation is the average distance of a single data value from the mean of all data values. Breakpoints for the ranges are based on these statistical values. For instance, the GIS would calculate the average of all US seasonal home values, and the standard deviation for them. Thus, when it comes to the percentage of the total housing stock that is seasonal, each state's percentage is an average of 3.1% away from the average state's percentage. These values for the mean and standard deviation of the values are used to set up the breakpoints. For instance, the breakpoint of the first range is all states whose seasonal home values are less than half a standard deviation value lower than the mean, that is, those states with the seasonal home percentage of less than the mean minus 0.5 times the standard deviation, or 2.34%. The fourth range consists of those states with a value greater than 1.5 times the standard deviation away from the mean. The other ranges are similarly defined by the mean and standard deviation values of the housing data. As figure 7.8 shows, the same data can produce choropleth maps that look very different and carry different messages depending on which method is used to classify the data. For instance, the map in figure 7.8d, or standard deviation, shows that most states have roughly an average percentage of seasonal homes, while the other maps show various distinctions between the states that are classified as having a higher or lower percentage of seasonal homes. Thus, the same data can result in different maps depending on the chosen method of classification. When you're selecting a method, having information about the nature of the data itself will help you determine the best kind of mapping. You should keep in mind that while different data classification methods can affect the end result shown in the choropleth map, the type of data values being mapped can also greatly affect the outcome of the choropleth map. An issue involved with choropleth mapping is displaying the values of data that can be counted when the sizes of the areas being mapped are very different. If you're mapping the number of vacation homes in each state, a very large state such as California is probably going to have a larger number of homes than a smaller state such as Rhode Island. This leads to making a choropleth map of the number of vacation homes in each state. California will show many more vacation homes than Rhode Island just because it has a lot more houses. A better measure to map is the percentage of the total number of houses that are vacation homes. In this way, the big difference in housing counts between California and Rhode Island won't be a factor in the map. Instead, you'll be mapping a phenomenon that can be comparably measured between the two states. When you map the percentages of houses considered vacation homes, California's seasonal homes make up only about 2% of the total, while Rhode Island seasonal homes make up about 3%. To make a choropleth map of count data, the data must first be normalized. That is to say, you have all count values brought onto the same level. For instance, dividing the number of seasonal homes by the total number of houses would be a way of normalizing the data. So there's lots more maps. A political map is a type of map that represents political divisions or human-created boundaries of the world, continents, and major geographic regions. Political features are characteristics such as country borders, roads, population centers, and landform boundaries. Political maps can vary in size and content. Physical maps illustrate the features of land and water within an area. They highlight such physical features as rivers, elevation, and water depth, as well as deserts and much more. Physical maps help us visualize what the land actually looks like by incorporating a description into the map. These are used for teaching urban planning and travel. Road maps are highly detailed maps with features selected to be of interest to a driver or someone finding their way. These maps highlight roads and intersections. They are not likely to exhibit additional information. Today, paper maps are disappearing because GIS technology can present maps that change as we drive, while a voice tells us what direction to turn. Topographic maps focus on showing the elevation of the Earth's surface. They do this through contour lines that link places with the same elevation. They often include names of natural features such as hills and hollows, and political features such as towns and roads. These are useful for hikers, planners, and natural resource extraction. Geological maps show the surface of the Earth if someone pulled off the soil and buildings. They mark the rock types that underlay the soil and show select geological features. Builders and planners use these maps to find a solid base on which to build. Disaster planners use geological maps to better deal with natural threats such as volcanoes and earthquakes. Choropleth maps show colors in areas to communicate where a variable occurs in place. These maps can show the results of an election, the spread of technology, or the ratio of cows to people. These maps are good for showing densities and ratios, but bad for nuance because they generalize over areas. Choropleth maps sound more difficult than they are. Isorhythmic maps include contour maps and other maps that use lines to join points of equal value. Color fills the areas between the lines, which make it easier to see where the values are the same. An isorhythmic map works well to display data such as air pressure on a weather map or plant hazardous zones on a CPAC. Chorochromatic maps are also known as qualitative area or area class maps. These are much like choropleth maps, except they ignore political boundaries. These measure a class, such as vegetation, that cannot be converted to a ranked numerical system. Chorochromatic maps are used to show patterns such as dominant vegetation, soil, or language. Dot distribution maps use dot to represent each case of the measured data and where it is located on the map. These dots can represent more case studies. A dot can represent 10 or 100 cases. Dot distribution map is great to show an accurate geographic distribution of data. One must create these maps with care. For example, if a dot represents zip code on a city map, you won't see a per house distribution. Proportional or graduated symbol maps are related to choropleth maps, but instead of color, they show the intensity of data through the size of a symbol. This allows the map to show a second data with them through the color of the symbol. This framework illustrates quantities better than ratios. This proportional symbol map shows the outcomes of the 2016 election, weighted by state population size. Decimetric maps are similar to the proportional symbol maps. They show dots representing data over a geographic background, but a decimetric map has a better way of representing populations. Moving dots to where people live makes a more accurate map. This method requires an additional step to adjust the dots to density. Cartograms rescale areas on a map to represent a count about a feature. You may have seen this in a world map where the size of the countries represents population, with a fat India These maps are great at showing numbers, but the reader has to have a basic understanding of maps in order for a cartogram to make sense. And then this is a comparison between two different kinds of maps that we looked at earlier. And that is everything I have for the lecture for this week. I'm going to just go over the final project real quick. So final project, you guys, it's already been assigned. You guys can access it. It's on my courses now. So feel free to take a look at it when you have some time. Basically, you guys are going to be creating a project for, you're going to be creating a product that uses our GIS technology, so a GIS related product. You don't actually have to go about making your product, but you do need to do the research, formulate a pitch, as well as have a brief write-up to go along with it. So I've provided this link for you guys. This is a couple examples. This is based off of the Esri Intern Hackathon. So these are all different GIS-based products that the interns from last summer made. So feel free to take a look at these. They're all really good. And then down here, there is the how the grading's broken up, and then what I will specifically be looking for each of the categories. So if you have any questions, do feel free to reach out to me. Aside from that, I am working on grading the midterm papers still. I'm hoping to get through a good chunk of them throughout this week and hopefully have them all back to you guys by early next week, if not over the weekend. There will be a quiz coming up. I will either assign it this coming week or it'll be assigned with next week's lecture material. It'll cover the last 3 sections. So it'll cover week 7 and then last week's content, which was technically supposed to be week 8, but it was actually week 10 since spring break was week 9. And then this week's content, which is technically week 11, but should have been week 10. So those are the 3 chapters it will be covering. So be on the lookout for that. I'll make an announcement once it is done. And I think that's everything I have for you guys. So with that said, have a good rest of your week. And as always, feel free to reach out to me if you have any questions or concerns. Thanks.